Okay, good afternoon and welcome to everybody. Welcome to the NITheCS Mini-school modeling optical spectra. I would like to thank Dr. Prof Tjaart Krüger very much for organizing this. And without any further ado, I'm handing over to Dr. Towan Nöthling. Thank you very, very much for your time. If I have it correctly, this is our last installment of this mini-school. Thank you very much once again. I can see that the YouTube recordings are really helpful. People are watching it. So please remember, share this with your colleagues. If people can benefit, please share. Thank you, Towan. Over to you. Have a wonderful session. Thank you. Tjaart, if you're happy.
Renee.
Thank you. If you please can handle the questions at the end, that'll be very helpful, Towan. Thank you. And thanks again for your time. And thanks for our attendees.
Thank you. I suppose you can all see my screen.
Perfect.
And the laser pointer. Thank you.
Thank you.
Okay, so today we are continuing our journey through the forest of spectroscopy with the focus on nonlinear spectra today. So to give you an aerial view of what we are going to discuss, we discussed how quantum dynamics inform spectroscopy. So for instance, we considered Exiton formation, and we also considered how fluctuations in the bath cause fluctuations in the system, and those fluctuations give spectral signatures. What we haven't spent much time on in the previous lecture is on describing excitation transfer dynamics and explaining how this type of transfer takes place is important for modeling spectroscopy, especially nonlinear spectroscopy, which will be the focus of today. So in the previous lecture, Prof Krüger discussed first the energy transfer for incoherent hopping, transfer of excitation. We will briefly consider first the transfer again. And based on this model for energy transfer, we will see how the correlation function and the spectral density characterize how the environment facilitates energy transfer. We will also then consider a coherent energy transfer model called the Redfield transfer method for excitation relaxation. Then we will consider nonlinear spectroscopy and how this relates to the nonlinear response function. We will discuss the third order response in particular, with two techniques based on this response, the pump probe technique and then two-dimensional electronic spectroscopy. The last part of the lecture I will spend on calculating the absorption spectrum. So this will be a very, let me say, extremely quick tutorial. I will also try to upload some code on the NITheCS website, but the code is included in this video as well. So even if the code is not uploaded, you'll be able to see this to see the code in the video. So I'll go through these calculations very quickly, but you can follow the code yourself. So last time I introduced the Fenner-Matthews-Olsen complex. Just to give you a recap, this is the photosynthetic system in green sulfur bacteria. Light is harvested by an antenna complex called the chlorosome, which contains many pigment molecules. The resulting excitations are transferred through a chlorophyll base plate and then through the Fenner-Matthews-Olsen trimeric complex, and finally to the reaction center from where energy-rich compounds are manufactured. So let's look at this Fenner-Matthews-Olsen trimeric complex. It has this form. It contains many pigment molecules in dark blue, and these pigment molecules are embedded in a protein structure. The protein is shown by yellow and purple ribbons. And here I show the pigment composition of one of these monomers. FMO, the Fenner-Matthews-Olsen complex, has 7 pigments. So in order to act as a conduit for energy transfer from the chlorosome to the reaction center, energy has to be transferred through the FMO complex. Last time, we considered the electronic Hamiltonian. The electronic Hamiltonian has the transition energies of the pigment molecules and also the dipole interaction between these pigment molecules. Now, when we derive the first method, we assume that this coupling, this interchromophoric coupling, is small, and we can treat this as a perturbation parameter. So when we do that, we get this description. What Förster theory describes is a hopping of excitation between pigment molecules. So if we start with excitation localized on pigment or site 1, here you can see site 1 is excited, while site 2 is in the ground state, then Förster transfer would occur by incoherent hopping of the excitation from 1 to chlorophyll 2. Okay. The Förster rate depends on an expression of is proportional to this expression, where R is the distance between the pigment molecules, and R0 describes the spectral overlap between the absorption spectrum of the acceptor and the fluorescence spectrum of the donor. So why does this spectral overlap feature in a description of spectroscopy, or sorry, in a description of energy transfer? Well, last time I discussed how the fluctuations in the environment, so let's consider the Fenner-Matthews-Olsen complex, how the fluctuations in the protein change the pigment transition energy. So fluctuations in the protein causes fluctuations in the energy, and these fluctuations one can think of as causing a continuum of states, which is described by a density of states function. So this spread of states gives more opportunity for overlap, energetic overlap between pigment molecules, resulting in transfer of excitation. So this density of states clearly has something to do with the correlation function of the transition energy fluctuations. Often we don't consider the correlation function, but rather the spectral density, which is the Fourier transform of the correlation function. The spectral density is a real function consisting of an even function and an odd function. We can write it in this form. And the odd function is independent of temperature. It describes the density of states of the nuclear states and also the strength of coupling between the system and the nuclear states. So often we will model this odd part of the spectral density using a model function. We can also obtain the full spectral density from the odd part. Like I said, we can model this odd part using some model function, usually or often this function has the form of an overdamped harmonic oscillator spectral density. In reality, this interchromophoric coupling is not small, so we cannot treat this as a perturbation parameter. So in reality, we have Exiton formation. So for instance, here I show the Exiton state alpha, which is this state in this figure. So an Exiton, again, is a delocalized state. So when we want to describe transfer or relaxation of excitation from Exiton state alpha to another state, Exiton beta, we have to describe the dynamics of the system density matrix, or in other words, the reduced density matrix of the system. So what happens is, if we start in an Exiton state alpha, over time, the population of state alpha will decrease and the population of Exiton state beta will increase. We will not consider the full system density matrix, but rather the population in the Exiton basis. That is we will consider only the diagonal elements or diagonal entries of the Exiton basis density matrix. The transfer of population between different Exiton states can be modeled in this way with rate constants given by this expression. The C alpha n describes the contribution of site n to Exiton state alpha. So what this expression tells us is that transfer of excitation from state alpha to state beta is facilitated by fluctuations on the energetic fluctuations on the shared pigments. So when we transfer excitation from state alpha to state beta in this figure, nuclear fluctuations on site 1 will facilitate this transfer. To give you a brief summary, in first theory, we considered incoherent hopping of excitation between individual pigment molecules, while in the Redfield method, we consider a coherent transfer between the Exiton states. We can describe the system density matrix, but usually we describe only the populations of the Exiton states using these expressions. Okay, now let's get to nonlinear spectroscopy. In the previous lecture, I showed you this expression. It says that the nth order polarization has to do with n interactions with electric fields and also with how the system responds to those electric fields. So if we were to measure the polarization at time t, we have to consider interactions with n electric fields in the past. This response function can be calculated using this expression. So we considered the linear response in the previous lecture. The second order response, second order signals usually disappear due to our orientational averaging in isotropic samples. So the lowest nonlinear response that we measure typically is the third order response. So in the third order polarization, or to describe the third order polarization, one has to consider three interactions with electric fields, and then also how the system responds through the third order response function. The third order response function has this form. Now, when we measure linear spectroscopy, we typically don't use pulsed light. What we do is we have a lamp and we shine light on the sample and we measure the absorption, say. But to calculate the third order response, we typically use electric field pulses. So these pulses are described by some envelope function. This is the black Gaussian functions that you see here, and then a carrier wave. There's also a polarization vector, which we will ignore in this lecture. So the signal field can also be described in this way. It has an envelope function and a carrier wave. What is important is that the wave vector of the signal is always a linear combination of the input wave vectors. And this makes sense. It's due to conservation of energy. The frequency is the same linear combination of the input frequencies. The signal envelope can be directly related to the third order response function. Okay, but how do we measure the signal electric field? Well, the best way to measure it is to have a fourth pulse. This pulse does not contribute in generating the third order polarization, but by looking at the interference between this fourth pulse, which we call the local oscillator, and the signal, we can determine the signal electric field. To illustrate this, let's look at the intensity of this total signal that we will measure. The intensity is the intensity of the combined signal and local oscillator field, which can be written in this form. The first part is small, since the signal field is already small. Third order signals are small. And then we take the square, so this is even smaller. We can disregard this term. The second term is known. And then we get the electric field of the signal in the third term. So now let's consider our first nonlinear technique, namely pump probe spectroscopy. So how a pump probe spectrum is determined is we measure we make two absorption measurements, and then we determine the difference of those measurements. For the first measurement, we use this setup. So we illuminate the sample with a light pulse, which we call the pump pulse. Then, a short time later, we illuminate the sample with the probe pulse, and we measure the absorption. From the signal that we measure here, from the absorption signal, we subtract the absorption that we measure using only the probe pulse. So again, first we use this setup to determine the absorption. And from this absorption measurement, we subtract the signal or the intensity, the absorption that we measured using this setup. For today, we will consider the difference in the intensity. So what we will discuss in the following slides can be applied to a difference in absorption as well, but it's easier for our purposes to discuss the difference in intensity when the pump is on, so this setup, and when the pump is off, this setup. Okay, so from these figures, it's not clear how pump probe is a third order spectroscopy technique. So we can make the correspondence clearer by considering this setup when tau1 is very small and tau3 is very small. This means that from the first two pulses in a third order spectroscopy setup, we create basically one pulse. And then we also let the third pulse coincide with the signal in order to create an interference pattern that we can measure. So this first combined pulse now, it's just one pulse, is called the pump pulse, which we describe using this expression, an envelope again, and the carrier wave. And the probe pulse using this expression, and the signal using that expression. The probe pulse is typically a broadband pulse, so it's typically white light or very broad in the wavelength region that you are interested in. We will also consider these pulses to have the same carrier frequency or central carrier frequency, so that the expressions are given by these expressions. Okay, so we detect the pump probe signal co-linearly with the propagation direction of the probe, which means that the signal wave vector, which remember is a linear combination of the input wave vectors, has to have this form or this form. So the pump wave vector has to cancel out because the signal wave vector has to be equal to the probe wave vector. And similarly for the frequencies. One can also write these expressions if K1 denotes the wave vector of the first pulse, K2 of the second pulse, but remember the first and second pulses are now one pulse. In future, we will only consider this linear combination. So when we measure the difference in intensity, that is when we measure the pump probe signal, first with the pump on, then with the pump pulse present, and then with the pump off, with the pump pulse absent, we get this expression. With the pump pulse on, we generate a third order signal, and interference of this signal with the probe pulse gives us this expression that we have seen earlier. Again, this first term will disappear because it is very small, and we'll only be left with these terms. We subtract again the intensity of the probe pulse, so that the pump probe intensity that we measure is given by this expression. Since the carrier frequency of the pump and the probe and the signal is, or rather the probe and the signal is identical, and also the wave vectors, we can write this expression in this form. So up to a phase factor, we can determine the signal envelope from this expression. Okay, but how do we use pump probe spectroscopy? To describe its use, let's consider a number of systems. I denote here the ground state with this black line, the excited state manifold, and then higher lying excited states. So let's start with the system in its ground state, or all of the systems, all of the, let's say, cuvette full of Fenner-Matthews-Olsen complexes, where each red circle represents one complex or one group of complexes. So let's start with all the complexes in the ground state, and then we pump the system. So we excite some of these complexes to the first excited state. Then we probe with the broadband probe pulse. Since the probe is broadband, it affects all of the complexes. So those complexes that were in the ground state after the pump will be promoted to the excited state, while those that are in the excited state can either undergo excited state absorption to a higher lying excited state, or those complexes can be de-excited to the ground state. Now let's consider the setup without the pump. So again, we start in the ground state, all of the complexes in the ground state. There's no pump now. So the broadband probe excite all of these complexes to the first excited state. And in a pump probe measurement, we have to calculate the difference between these two measurements, with pump and without pump. Just inspecting these last two figures with your eyes, you can see that this is the difference that we obtain. So there's a stimulated emission contribution from this first excited state to the ground state. There's also an excited state absorption emission, and then something that we call the ground state bleaching term. To understand this, let's think in terms of absorption again. So to measure pump probe, remember we measure the absorption with the pump on, and then subtract from the signal the absorption with the pump off. So when some of the complexes in this with the pump on has been promoted from the ground state to the excited state, then subsequent excitation by the probe pulse will see less complexes in the ground state, meaning that there is less opportunity for absorption to happen, and we get the ground state bleaching contribution. When we plot this difference in absorption, we see an excitation, excited state absorption contribution, which is positive, and then negative ground state bleaching and simulated emission contributions. Now, let's go to the second technique that we will consider, namely 2D electronic spectroscopy, two-dimensional electronic spectroscopy. Now we consider this setup. We have the 3 input pulses again, and these input pulses illuminate the sample from different directions, as illustrated in this figure. This is called the boxcar setup, named after a train car. And the local oscillator, which remember does not participate in generating the third order signal, it's just there to measure an interferogram. The linear oscillator, or the local oscillator, comes from another direction. And we measure the signal in the direction of propagation of the local oscillator. So you can test for yourself that this linear combination corresponds with the figure as shown here. So the signal wave vector that we measure has this linear combination of the input wave vectors and this linear combination of the input frequency. Now, we can control these times, or at least detect these times. We have control over the time between pulse 1 and pulse 2. In an experiment, we can control those times by placing a glass wedge, for instance, in the optical path, and so doing slow down the propagation of the light, or build a delay line or whatever, but we can control time 1 and time 2. And we can also detect the time since the third pulse and the signal by shifting the local oscillator. As I said, we calculate the third order response function, and the signal electric envelope, or the electric field envelope, can be calculated directly from the third order response function. Now, in this particular setup with these wave vectors, we measure only the so-called rephasing third order response. It's called rephasing since during time period tau 1, the unitary evolution is in a direction opposite to what it is during time period tau 3. So the system sort of rephases itself. So the rephasing third order response can be given as a sum of these 3 terms. Don't worry about the notation here. But these contributions can be described in terms of the system density matrix. So in the form of so-called Feynman diagrams. To read these diagrams, note that time increases from the bottom to the top. So the top happens later than the bottom. And we start with the system in the ground state. So we start with this density matrix, or this density operator. And each of these contributions denotes a different interactions with the system density matrix. So for instance, in this R2G contribution, we start in the ground state, then we act on the bra side of the density matrix with one of the electric fields, then on the ket side, then on the bra side again, and ket, and so on. Inward facing arrows denote absorption events, while outward-facing arrows denote emission events. So here you can see the simulated emission, ground state bleaching, and excited state absorption contributions to the third order signal. We can also represent these contributions in this form. It's maybe slightly easier to interpret, but it's not, it doesn't contain all the information that the Feynman diagrams contain. So to explain this diagram, we will first have an excitation from the ground state to state alpha, then an excitation from the ground state to beta, then de-excitation from alpha to the ground state, and de-excitation from beta to the ground state. Again, alpha and beta denote the single exciton manifold, while F denotes higher lying excited states. So I haven't yet shown you an actual spectrum. So how are 2D spectra generated? Well, we start off with a data block in terms of tau1, tau2, and tau3. So as a function of these times, we get the electric field, the third order signal field. So one can think of this as a data block containing the electric field signals. Then we Fourier transform over time tau1 and tau3 to get a data block in terms of omega1 and omega3 and tau2 along the third axis. We will also call tau2 the population time. One can think of this data block as the y-axis denoting the excitation frequency, the x-axis denoting the emission frequency, and this other axis denoting the time, the population times between the second and third pulses. So what we get is data like this. We get a spectrum, omega1 versus omega3, and we get different spectra as a function of the population time, as a function of this tau2. Here, this front spectrum shows the 2D spectrum at time 0 femtoseconds, whereas this second spectrum shows the spectrum at tau2 50 femtoseconds. What I forgot to measure to say is that in a 2D spectroscopy experiment, these pulses are very short. So they have a duration on the order of 100 femtoseconds or so. Okay, so let's look now at a couple of these 2D spectra, namely the 2D spectrum at 0 femtoseconds for tau2, at 50 femtoseconds, and at 2000 femtoseconds. What can we learn from these spectra? Let's again consider the FMO complex, the Fenner-Matthews-Olsen complex. Well, one of the Feynman contributions, one of the Feynman diagrams, is that of the SE, the stimulated emission Feynman diagram. And during the population time, we start off in this population of in a population of Exiton state alpha. And if we make T2 tau2 large enough, so if we consider this as a function of time, then the population of Exiton state alpha transforms into a population of Exiton state beta. In other words, excitation is transferred from Exiton state alpha to Exiton state beta. This excitation transfer, of course, can be modeled using the approaches we discussed earlier, for instance, using the Redfield method. In in this example, remember that the y-axis, one can think of that as the excitation axis and the x-axis as the emission axis. You can see that at initial times, when we excite at a high energy, we will also emit at a high energy. But with time, that excitation is transferred to lower lying states, so that when we excite at high energy, the excitation flows towards lower energy states, so that by later times, if we excite at high energy, the population has time to relax to a lower energy state from where it emits. We can also do something else. We can consider the 2D signal as a function of the population time, so as a function of this tau2 time. So here I show as a function of tau2 the 2D signal at the position of that black cross. And you can see some clear oscillatory behavior. So again, showing the simulated emission Feynman diagram. In the period of tau2, you can see that the unitary evolution causes this oscillatory behavior of the signal, which points to a superposition state. So a superposition of state beta and alpha. There has been some heated debate on whether this superposition is electronic in nature. If it were purely electronic, then it could mean that plants perform some sort of quantum computation algorithm in order to optimize photosynthesis. Well, plants or green sulfur bacteria, as in the case of the Fenner-Matthews-Olsen complex. But it is unlikely that the superposition that results in the oscillatory behavior is purely electronic. Rather, the superposition is likely between vibrational states on the same pigment molecule, or a mixture of electronic and vibrational coherences or superpositions. And since these vibrational levels are on the same pigment molecule, they can't contribute to excitation transfer between pigment molecules. So it's unlikely that this oscillatory behavior points to quantum computation in photosynthetic systems. Okay, so to give you a summary, we considered the third order response function, which is given in by this expression. We then saw that the nonlinear signal can be written in this form, and we can get the envelope function directly from the response function, the third order response function. The signal wave vector is a linear combination of the input wave vectors, and so too is the signal frequency. Using something called heterodyne detection, I didn't mention that name earlier, but basically using interference between the signal electric field and the local oscillator field, one has information directly of the signal electric field. Then we looked at pump probe spectroscopy. We considered this setup, and we saw that the pump probe spectrum, the pump probe signal, can be interpreted in terms of different contributions, namely ground state bleaching, stimulated emission, and excited state absorption, which gives these spectral forms. And then one can do further analysis to determine what signal in the to deconvolute the signal into these different contributions. We then discussed 2D electronic spectroscopy. We used the boxcar setup and saw that we can generate 2D spectra as a function of the so-called population time, or tau2. Okay, so that concludes the section on nonlinear spectroscopy. Now this is a mini school about spectroscopy, so we have to calculate something. I will very briefly discuss how we calculate an absorption spectrum. So we are back to linear spectroscopy now. Let's calculate an absorption spectrum. Like I say, I will go through this calculation very quickly, but there will also be some code available with which you can generate your own absorption spectrum, and you can look at the code, and if there's any uncertainty, you can contact us. So we said in the first lecture, or in the previous lecture, that the absorption spectrum can be written in this way. It depends on something that we call the dipole factor matrix and on the spectral tensor. Now, when we perform a second order cumulant expansion and we make the secular approximation, those names won't mean anything to you now, but if you come across them in literature, we get this expression. And this expression we can use for calculations. So the stop expression is given in the site basis, in the basis of localized chlorophyll excitations. But after making the secular approximation, we have to work in the Exiton basis. And all transformations between the site basis and the Exiton basis can be made through matrix diagonalization procedures using Python, for instance. And we can calculate again we will calculate the absorption spectrum for the FMO complex. So first, we need access to the dipole moments, or the dipole strengths, which are just the square root of the magnitude of the dipole moments. We get that information for FMO from something called the protein data bank, and we assume that the transition dipole moments is parallel to this axis, to the so-called NB, nitrogen B, nitrogen D axis. This also won't make much sense, but know that we can extract the dipole moments for the bacterial chlorophylls from something called the protein data bank. And we can transform the site dipole moments into the Exiton basis dipole moments using this expression. We can calculate the Exiton energies directly by diagonalizing the Hamiltonian. And then there's something called the line shape function, which we calculate using this quite monstrous expression. The line shape function depends on the spectral density, and we can calculate it by using just the odd part of the spectral density, which we model using some model spectral density. For instance, we can use the spectral density of an overdamped harmonic oscillator with suitable parameters. And again, we can transform this site basis quantity into an Exiton basis quantity using the transformation matrix. Again, the IN denotes the contribution of site N to Exiton I. The last term has to do with population decay of the exciton. So when excitons relaxes, excitation is transferred from higher lying states to lower lying states, causing the higher lying states to have a finite lifetime, and this finite lifetime basically brings about a uncertainty in energy, which we have to account for in the spectrum. So this lifetime contribution can be calculated by summing the rates. So we calculated the rate field rates earlier. So we will calculate these rates as rate field rates using this expression that you have seen, making use of the spectral density. And the spectral density, of course, can be calculated from only its odd part using this expression. Okay, so I will upload some code to the NITheCS website, but if the code and the video get separated somehow, I will just quickly show the code. So we start with a Hamiltonian in site basis. So this is the energy, the top left entry is the energy of pigment 1 in the FMO complex. And this quantity is the coupling between pigment molecules 1 and 2. Then we also extracted the dipole moments, and we use a function to generate a model spectral density. This just calculates the odd part of the spectral density. We also have a function to calculate the line shape function. And we can calculate the rate field rates matrix. We can then use these quantities, or rather we can calculate these quantities using some model parameters. And then finally calculate the spectrum using the expressions that I gave earlier. So using this code, we can generate this absorption spectrum for the Fenner-Matthews-Olsen complex. Yeah, so you are welcome to play around with the code and see, yeah, investigate the code, and if there are any problems, you're welcome to contact us. Just to give you some resources for two-dimensional electronic spectroscopy, these are both good review articles. This article in Nature and this in BBA Bioenergetics. Okay, and these resources I showed you earlier in the previous video. I will especially recommend watching this series of lectures on YouTube about nonlinear optical spectroscopy by Prof Tomasz Manchel. So thank you, and I also wish to thank you, NITheCS, Renee and Prof Petrociani, for giving us this opportunity to hopefully give you some sense of spectroscopy. Thank you. Any questions?
Right. Thank you very much, Towan. You have covered a broad range of topics, and we have plenty of time for questions. I would like to open the floor for questions, and you don't need to limit your questions only to this lecture. You're welcome to ask about any of the lectures that we have presented. So from the first lecture, actually the first two, where we've laid some foundations to the modeling of spectra, introduced some basic concepts, and also the last two lectures where the focus was on linear and nonlinear spectroscopy. So any questions are welcome. And while you're thinking about questions, I'm adding a link here in the chat. If you would like to access our lecture slides, and I understand the code that Towan has referred to in the last few slides will also be loaded there. So you're welcome to have a look there. Not all the lectures are there yet, but I'm sure the complete list will appear there very soon. Okay, there we go. Okay, so any questions are welcome.
Maybe I should start again.
Yeah, so if you need more time to go over the lecture material and you can't formulate a question now, you're welcome to contact us at any time. And I see Francesco has appeared. Francesco, you're just in time for the Q&A, which I've started to handle. So I can handle the first question and then I can give over to Francesco. So we have a question from Michael Mwalaba. He asks, how did you generate the numbers you used to plot the spectrum?
So I suppose you mean this spectrum. Well, I generated the spectrum using the code that I will make available. This code takes as input some parameters that we can extract from a protein database, for instance. And it also makes use of a model spectral density. Yeah, and then I just use the expressions that I showed on these slides. So I think this will take some time to digest. If you are interested in generating your own spectra, you're welcome to go through these slides again and use these expressions to calculate spectra. Yeah, I hope that is clear. If that is not what you meant with your question, please, you're welcome to ask again.
Any other question or any follow-up question? I see the attendees are quiet today, so either everything was clear or they
Or
need
nothing
more
was clear.
or they need more time to go through the material.
Yeah.
Okay, the name of the code, can you repeat that, Towan?
It doesn't really have a name. It's just code that I wrote, so I will make it available. Yeah, it doesn't really have a name. Currently, the file name is I don't know, some cryptic name, but I'll rename it and make it available.
You know, and we will be very happy to share it through the NITheCS website and advertise it. Yeah.
Thank you. That was a question that I had whether it can be uploaded. Okay.
One PhD student of mine also produced a software package of sorts, and it's on GitHub, and it's freely available to everyone, and we keep advertising it. Yeah, so you're welcome to share it with us, and we can advertise it. That would be great. Yeah.
Thank you. This is just a small little script to illustrate the calculation of spectra. So yeah. It can even just be uploaded in one single text file.
We can upload it next to the slides of the mini school. That would be also,
yeah, that would make sense. Yeah.
Yeah, we'll be very happy to do so. Yeah.
Thank you.
Excellent. And I need to apologize. I missed most of the mini school today because I had to take care of some visitors that popped up more or less unannounced. But I'm sure that it went well, and thank you very much to both of you for putting this together. So thank you very much. I'm sure that the video will be online by tomorrow, the day after tomorrow, and we will upload the slides as well and the code, and we'll keep advertising it.
Thank you very much, and thank you for the opportunity.
No, thank you guys. Thank you very much, both of you, for putting together this very nice course. Thank you.
Yeah, it was a pleasure, and thank you, Francesco, for allowing us, giving us this opportunity.
You know, we're always looking for volunteers, so thank you very much. Yeah. You're welcome to organize a follow-up course anytime. Yeah. Thank you. And you see there are lots of claps coming towards you. Excellent. Yeah. Good. Wonderful. Then thank you very much. Thank you very much for your time. Thank you very much to the participants. And yeah, and I think the announcement for the next mini school should go out today or tomorrow. Yeah. So please keep following NITheCS, and I'm sure we will have another exciting mini school next month. Thank you very much, everyone. Have a good rest of the day.
Thank you.
Bye-bye.
Thank you.
Bye-bye.
Goodbye.
Bye.
Bye.